Every construction project starts with a clash between nature and engineering. Before you can build, you have to take unpredictable, sloping terrain and force it into a perfectly flat, stable foundation. But before a single piece of heavy machinery arrives on site, contractors face a massive financial risk. They must know exactly how much earth needs to be scraped away and how much needs to be brought in. To get those numbers right, we are going to break down 3 essential skills: reading topographical maps, establishing survey grids, and executing spot height mathematics. Nailing this mathematical workflow is exactly what separates a highly profitable job from a complete logistical disaster. This diagram illustrates cut and fill. Earth is removed from the high side of a slope, the cut, and placed on the low side, the fill. The goal is to reach this dashed line right in the middle, the finished platform RL, or target baseline elevation. Here is where beginners make their first major mistake. When you dig soil out of the ground, it expands. It loses its natural compaction and traps air. This means your final pile of excavated dirt, known as spoil, takes up significantly more volume than it did in the ground. The amount of expansion depends entirely on the material. Clay, for example, typically expands by 22%. That requires you to multiply your excavated volume by a bulking factor of 1.22. If you calculate 100 cubic meters of cut, but ignore the bulking factor, you will end up staring at 122 cubic meters of loose clay on site, and nowhere near enough dump trucks ordered to haul it away. To calculate cut and fill, we read the terrain using contour lines, connecting points of equal elevation. Tightly packed lines on the left indicate a rapid drop, or a steep hill. Lines spaced far apart on the right mean the slope is gentle. There are 2 strict rules for mapping these elevations. A contour line will never split into 2, and contour lines will never cross each other, unless you are mapping a perfectly vertical cliff. If you pull these lines straight up into the 3rd dimension based on their elevation values, the physical shape of the landscape instantly appears. Decoding the spacing and elevation of these lines is step 1. You cannot mathematically grid or survey a site until you understand the basic shape of the ground beneath your feet. Natural terrain is organic and chaotic. To calculate exact volumes, we have to impose order. We do this by laying a rigid geometric grid over the entire excavation area. This chart breaks down the grid method. Step 1 in the field is setting out a straight baseline along a single edge of your irregular survey area. From there, you establish secondary lines at strict 90-degree angles to that baseline. You project these out to form a closed, rectangular boundary that fully encapsulates the site. Finally, you place pegs at regular intervals to create an alphanumeric grid. You then use a level to record the exact elevation, the spot height, at every intersection where those lines cross. We have now replaced unpredictable slopes with a standardized network of data points. Every coordinate has a defined height, giving us the raw numbers needed for the final volume calculation. Imagine each square on that grid acting as the top of a column, extending straight down into the earth until it hits our finished platform level. These columns form 3D rectangular prisms. To find the volume of one of these columns, you calculate the depth at its 4 corners, average those 4 numbers together, and multiply the result by the surface area of the grid square. Doing that math for a single prism is easy. Doing it individually for 50 or 100 prisms across a large commercial site is slow, tedious, and opens the door for manual errors. This table demonstrates the industry solution, the collective depth method. Rather than treating every prism separately, this spreadsheet tracks how many times each individual corner is shared across the entire grid. Look at the number of uses rule at the bottom. If a spot height sits on the absolute outer corner of your total excavation area, it only touches 1 prism. Its number of uses is exactly 1. But if a point sits on the outer edge, it is shared by 2 adjacent prisms. And a point sitting right in the interior of the site forms the corner for 4 separate prisms simultaneously. Instead of repeating calculations, you multiply each spot height by its total number of uses. You sum those collective depths, divide by the total number of uses across the board, and multiply that single average depth by the entire site area. This collective calculation eliminates redundant math. drastically reduces your chance of making a spreadsheet error and gets you to the final volume in a fraction of the time. We started with uneven, organic terrain. We mapped its slopes, established a rigid geometric grid, and processed spot heights to find our exact cubic volume. Before you make any phone calls, take that final number and multiply it by your soil's bulking factor. You have to account for expansion. With that adjusted volume in hand, you know precisely how many trucks to order and how long the excavation will take. You can price the job accurately.